right, welcome back, Physics 325. We're on video 2 now of week 10. This week we're talking about imaging, and this video we're going to talk about imaging instruments and instrumentation. So we're going to start with the most complicated imaging system of all, I think. The human eye, pictured here, is an incredibly sophisticated thing, and we're only going to get the basics of it, but we will have a talk about it from you guys next week, I believe, so we'll hear maybe a bit more about it then. For now, let's just look at the basic properties of it as an imager. So the first thing to note is that it has a lens. And from last video, we found that a lens is a point-to-point mapping system. It forms images. And one interesting thing about the lens from last video is as follows. It focuses an image at a point. Now, where it's going to focus the image in this case is going to be on the back of the eye, the retina. And it's going to map all the points in the outside world onto your retina to form an image. One thing weird about that is, as we found last lecture, that depends on how far away you are, right? So if we have a lens with a given focal length f, and an object I want to look at, we can draw our principal rays and find that that is going to get mapped to an inverted image. We have the object distance here, focal distance here, and the image distance here, such that 1 over the focal length is equal to 1 over the object plus 1 over the image distance. Therefore, for a fixed focal length, the image distance, where it is, and in this case, it better be on your retina, well, it depends on how far away you are from the object. Now, this is a big problem. How does nature get around this? Well, it has a variable focus lens, which is amazing. And that's a phenomenon known as optical accommodation, okay? There's actually a neat video on how this works. So if the muscles, called the ciliary muscles here, are fully contracted, that makes the lens maximally bent, and then we have the strongest lens. So as we see here, if we have a fixed location, and we bring the object closer and closer, just from geometry, we're going to have a tighter and tighter focal length lens, a stronger lens. And that is given by this optical accommodation, and you can try this right now. Pick up something, anything you'd like, and look at it on your, whatever you can find on your desk. Bring it closer and closer and closer. You're going to feel it. Feel for that strain. You'll feel your eyes strain at some point, and then notice lose focus. Okay? Bring it away. I'm probably older than all of you, so it's going to be further away from me than for you guys, but if you see that, there's going to be one point where you can start feeling the strain, and then it'll lose focus. That is what happens when your eyes are fully contracted. And that point where you lose focus is called the near point. Now, there's a survey done at some point. I don't know how they conducted this, but there's an average standard of 25 centimeters. But it can be very different. For example, toddlers or 5-, 6-year-olds, they might have a near point as close as 4 centimeters, whereas elderly people will have it a meter away, 100 centimeters away. So they'd have to read like this without wearing glasses, okay? So that's if the ciliary muscles are fully contracted. Now suppose they fully relax, so the lens becomes less and less. It has a larger radius of curvature, meaning it's a less tight focus. Well, that's what you call the far point. Ideally, that far point is at infinity, so that when your muscles are completely relaxed, in other words, you're looking at objects at infinity or very, very far away, the focal length of your lens should be right at your retina. That's where the images will be formed. If your far point, when you're fully relaxed, is not infinity, that's called farsightedness, and you need glasses to correct for that. So we might hear about that in the student presentation. So now let's talk about the receptor part of this, okay, what's going on in the retina when you're actually somehow processing these images. You have about 100 million of these receptors, and as we found in an earlier student presentation by you guys, these come in 2 flavors, rods and cones. The rods are very sensitive to light and fast motion, whereas the cones come in 3 flavors, red, green, and blue. and they detect the sensation of color. They're mostly concentrated in this region called the fovea, which is where images looked at face on are imaged. So the corner of your eyes are more sensitive to slight variations in light from the rods, and they have a bit better light sensitivity, whereas the central region, the things you're looking directly at, will have that color sensation. And that happens primarily on the fovea. One very interesting thing is how that image information gets sent to your brain. Now, venturing into biology, I'm not a biologist, from a naive physicist point of view, we can see this as a data processing and a data compression system, because we have about 1 million optic nerves and 100 million receptors. So we actually already have some pre-processing going on as that information is getting sent to your brain. Quite a lot, actually. Now here's an image from Wikipedia of what the image, the actual physical image on your retina looks like. So notice that it's only in focus at one point. There's a blind spot, as it's called, where your optic nerve comes in, and it looks severely distorted. Most importantly, this is the fact that a lens is only going to focus at one point, so you can only look at one distance at a time. This is what you guys would see looking at this fellow. However, you don't notice that. You have this vivid sensation of color. Now, you can actually simulate the blind spot yourself if you want. You actually, can detect, not simulate it. You can actually measure it by putting something about, I don't know, maybe 3 or 4 centimeters away on your desk. Draw a little circle and an X. Try this on a piece of paper. And then cover your right eye and look at around the X. Back and forth, move it around. There it is about for me. This circle somewhere here is completely gone for me now. So you can actually, I urge you to try that right now, detect where your optic nerve comes in, where the image is. That is called the blind spot. Okay, a lot more to say about the eye, but this is where we're going to leave it as a simple, looking at it very simple-mindedly as an optical instrument. Let's move on to a very simple one now, an actually simple one, a simple magnifier or a magnifying glass. This is a simple magnifier, a magnifying glass. First thing we need to ask is, what is the magnification of this? We already have a picture drawn up here which tells us. So we have this stick figure with height h of the object, and it's a distance do away. We have a triangle here, ho over do, okay? So what is that magnification? It's going to form an image, hi di away, and we're just going to define the magnification as how much bigger it is, how much bigger the image is, or smaller than the object. And we see that from this triangle here, along the line to this triangle, these two triangles are similar, meaning they have the equal ratios of opposite over hypotenuse and opposite over adjacent. So hi over di, this holds. And therefore, we can say that, we can notice that this is inverted by geometry, and we can see that our magnification, which is the image height over the object height, is equal to the image height over the image distance rather over the object distance with a minus sign. Okay, so that is the magnification of a lens. Now, that's the magnification. That's how big an image is. But let's think about what it means for an image to be big, right? It's really about how much angle it takes off. If you have your hand over here, it looks smaller than somehow if you bring it close, it takes up more field of view. So how big an image is according to your eye with a fixed retinal space is how much angle it actually takes up, how much field of view. So let's do an experiment here where we have this fellow here, and he's terrified of bugs. So we're going to put a bug over there. And notice one thing, that the actual angular space taken up depends on a few things. So the height on the retina depends on the distance to of the image, which is fixed, that's the length of his eyeball, times the object height divided by the object distance. So we can either make the object very tall, or we can make the distance very small. We can bring it closer. And as we do that, both will have the effect of making a larger image on the retina, taking up more space. So I'm sorry, but we're going to do this cruel psychological experiment to you, and bring that bug closer. Now, this person it will appear, according to his eye, that it takes up as much field of view as a giant bug that is correspondingly further away. So we can make an object as big as we like this way, or can we? So first of all, I don't want to put it on this poor fellow's eyeball, but before that, we've just found out that that's going to be an issue, right? If I bring something closer and closer and closer, it'll eventually become blurry, and I won't be able to to accommodate it. My eye will not be able to form a strong enough lens to bring it to focus on my retina. So there's a limitation to how big you can make something with magnification, given by your how strong your lens in your eye can be, right? Given by the near point. Okay, and that's where the magnifying glass comes in. Effectively, what we're going to do is we're going to build a stronger lens by placing this thing right next to our eye. We can bring our near point even closer. What's actually going on here is we're bringing an object as close as we can. We're going to use a lens to form a virtual image of it, and we're going to look at that virtual image. So if you have a little cheap magnifying glass lying around, give that a shot. But here's our textbook here. And I'm going to show you, for me, this is about how close I can get it. I can get it about this close before it gets blurry. Okay, so about there. I'm going to put this in front of my eye, and it's in focus about here. So I can really bring this much, much closer. And I just noticed there's a little diffraction pattern right in the middle of the C there. Thanks to my magnifying glass. So that's what's going on with the magnifier. You're effectively bringing your near point closer. And as you see those old Sherlock Holmes detective cartoons with magnifying glasses, if you guys have ever seen pictures of those, their magnifying glass, if held correctly, is right in front of their eye, and they're kind of snooping around this way. So since we have a lens, we have an adjustable lens, we get to actually choose where that virtual image wants to go. Let's put it at infinity, okay? So negative infinity, it's a virtual image. Image distance goes to negative infinity. We cover this, right? And the object distance is f, okay? So what is our magnification? How much has this helped, right? Well, before we could get it 25 centimeters away. Now we can get it roughly a distance f away, right? Because if that image distance is at infinity, the object distance, the new one, is roughly the focal length of that lens. And from this formula, we have a magnification of 25 centimeters over f. And this is how the magnification of a magnifying glass, a simple magnifier, is defined. It's defined anatomically in a way based on the rough average near point of 25 centimeters for human adults. Okay, and that's a simple magnifying glass. But we can do a bit better than that. We can do better with what is called a compound microscope. It's a similar approach, but we're going to use two lenses now. The first thing we're going to do, I can see if I have another lens around here. Yes, here's one. Now, a compound microscope uses two lenses, okay? It has a big lens called an objective and a smaller magnifying glass called an eyepiece. Now, it's not so important for this course to understand all the nuances of compound microscopes, but what you should understand is the basic functionality. So what we're going to do is we're going to take two lenses to make a better image, and we're going to use a two-step process. So step one, what we'll do is we'll form a real image of a very small object. Okay, we're going to form a real image of something small that we want to look at, and that's going to come out here somewhere. Okay, so let's think about that. Here's our bug. It forms a real image here, and it has a given magnification, just given by the thin lens formula. Okay, so what is our object and our image length here? Well, it turns out there's a standard here. There's a standard, what is called tube length, which is defined as the length from the focus to where you want that image to form in a microscope. This is just something that has been invented as somewhat of a standard. So given that, it can be shown, and this may be a quiz question, that this leads to the following magnification. We have the image to the image distance divided by the object distance, and that's equal to the tube length L, 16 centimeters in this case, divided by the focal length of the objective. All right? So that's step one. We've created a real image with our objective lens. Step two is magnify that with a magnifying glass. So my compound microscope, I have kind of a crummy one here, 50 centimeter objective. but I'm going to form a real image, and then I'm going to try to magnify it, and there you are. I see a very decent sized upside down D here. So what's going on there is basically I have that real image, which I can now form an image of with my magnifying glass as follows, right? So that's going to form a virtual image behind the lens, and it's going to be much bigger, right? And we get an additional magnification. We've already figured out what that magnification needs to be, okay? So we get a total magnification. So first we blow it up by a factor of 16 over the focal length of the lens, and then we blow it up by 25 over the focal lengths of the eyepiece, okay? We get a total magnification of 16 times 25, or 400 centimeters squared, divided by the product of the eyepieces. So this is what a typical compound microscope looks like. So I have these eyepieces here. There's two of them. It's a binocular eyepiece. We have our 16 centimeter tube length here. It hits a mirror, and it goes down to an objective. And it seems I can choose multiple objectives here. And this is what the eyepiece looks like. These objectives are very tightly focused lenses, and the eyepieces are just simple magnifiers, okay? Let's try to pick apart this. I don't know if you guys can see this. This says it's a 20 times magnification. What is the focal length of this magnifier? Well, it said 20x, and that's equal to, so 20 is equal to 25 divided by f, right? So the focal length in centimeters of that magnifier apparently is 25 over 20, which is 1.25 centimeters, okay? Is that reasonable? It's pretty close, but it does look like I form an image. I buy that, about a centimeter or so behind that lens. I had doubt for a second there, but that appears to be legit. So a real 20 times magnification. How about the objectives here? Well, we have this one, for example, which it says 4x on it. And we have another one that says 10. So think about the 4x magnification. So we have, that's the focal length of the eyepiece, by the way. We have 4x is equal to 16 centimeters over the focal lengths of the objective here. That's a very wide angle, low magnification, but it seems here that the focal length of the objective in that case is equal to 4 centimeters, just under 2 inches. And we can see that that's probably pretty reasonable from this distance here. So what is a total magnification in that case? Well, it's 20 times 4. Putting these two together, I get an 80 times magnification. Okay, I can get higher magnification eyepieces, but really it's about getting the optics clean for this objective. The best one I have is a 100x oil immersion lens here, which would be able to really zoom in on things with a smaller field of view. Okay, so the final thing we want to talk about today is astronomical telescopes. Okay, the goal is to image very distant, very faint object, and they're so faint that photons are at a premium, right? Stars, I mean, we can see them, the ones that are in the sky, but if you look through a telescope, you can see far more stars that weren't there, that were below the threshold that the human eye can detect. By the way, I didn't say that. There's experiments showing that as few as several photons, like on the order of 4 or 5 photons at a time, can be detected. Anything else gets processed as noise by your eyes. So what if there's just not enough? What if the intensity of that light that's so far away due to that 1 over r squared term that we talked about earlier in the course, such that the mean photon number is less than a few? We just won't be able to see it with the naked eye. Well, what we can do is get a bigger eye. Well, I can't actually get a bigger eye, but what we can do is we can get a big lens and somehow focus it into our eye while maintaining the integrity of the image. And that's precisely what an astronomical telescope does. Think of it as a bucket for light. We want to collect as many photons as possible. Now we'll talk about just a simple implementation of one. There's many such implementations. I believe it says Newtonian here, but this one might be the Galilean, so take that with a grain of salt. Okay, so we have our refracting telescope here. Let's think about how this actually works. We have a beam coming in with a given diameter. We have a plane wave, and we're looking at some area of the sky, right? So we get some area, we get that much of the plane wave coming in. What we're going to do is we're going to condense it and then recollimate it. So it's coming in collimated, we're going to condense it and recollimate it. We can do that by having two lenses separated by their focal length. So collimated rays come in looking like this. They get squeezed down to a narrower waist, okay? We use this all the time, not only in astronomy, but in the lab to change the width of a laser beam. It's called a beam condenser or expander. And the whole idea is if they're separated by a focal length, we have width 1 coming in. We have a tighter focus here. We're going to have a narrower beam. So it's the same number of photons that have come in. If we look at the front view of this, we have this area, pi r squared here. That many photons, that's just given by the intensity from the star, the flux from the star, has now been squeezed into a smaller area. So we're actually increasing the amount of photons per square centimeter in that region there. Okay, so that gives a given light collecting power and light collecting enhancement. All right, so the idea is that we'd like it so that that beam exit size is as big as our CCD or our eyeball, and we've effectively take the ratio of that output waist from the input waist. The input waist to the output waist gives a ratio of diameters, and the area, right, that's what gives the flux, is proportional to that squared. So if we have a, if we have a 5 millimeter eye or a 5 millimeter CCD, for example, and a 500 millimeter input lens, well, we have a factor of 100 in radius, therefore 10,000 times the amount of light per pixel on the CCD or per area in your eye. Now, anybody who's looked at the moon or an object in the sky will also tell you that it looks bigger somehow. So how do we talk about the magnification of a telescope? Well, you can kind of draw a sketch on how that would work. Okay, so this is a sketch of what you'd get. These two objects, the blue and the red one here, A and B, they separate with some angle. They're going to come in collimated, they're roughly at infinity, so the beam is coming in collimated from both of them, and therefore from our telescope configuration, we know they leave collimated. So we have a given angle here. What angle did they take up? With these rays will meet here, the objective away, right? They're going to come to focus at the objective, and that's going to take up some height, h, whatever it is. Similarly, the same h, that by the way is what we call our input angle, okay? Now that same h here, with this triangle here, is our output angle, and it similarly is given by, well, if this one is h over f objective, this one is equal to h over f of the eyepiece. Okay, so alpha out over alpha in, which is what we're going to call the angular magnification, is given by, well, let's just draw it out. It's given by h over fe divided by h over f object. So that's the objective focal length divided by the eyepiece. And that's the magnification, the angular magnification of a telescope, a refracting telescope is drawn here. Okay, so that's it for the instrumentation that we're going to talk about here. So just to summarize, we started with the human eye. Okay? So we had this variable focus optical instrument that accommodation allowed for that, and we still had image formation by our lens. The closest you can get something when your ciliary muscles are maximally contracted and you have the tightest possible focus, that's called the near point. When they're fully relaxed, we have the far point, which should be at infinity. By convention, the near point is at 25 centimeters. How do we improve on that? If we want to look at something very, very close, we get a magnifying glass. So a simple magnifier. And what we get there is we form a virtual image, or equivalently bring our near point closer. And since our near point started at 25, we can now bring it closer, a distance f away. That leads to this definition of the magnification of our simple magnifier. Okay, We can improve on that with a two-lens design known as a compound microscope. First, we're going to form a real image with an objective lens, and then we're just going to use a magnifying glass on that real image. And those two magnifications multiply, they combine, right? It's n times bigger than m times bigger, and we get a magnification of 400 centimeters squared divided by the product of the eyepiece and objective focal lengths. Finally, we talked about a very simple implementation of an astronomical telescope, where the goal is to collect as many photons as possible. That yields a light collecting power of f objective divided by f eyepiece, the objective lens's focal length divided by the eyepiece, squared. So it can be very pronounced. And we also have an angular magnification of the objective focal length divided by the eyepiece. So that's it for this lecture. We'll do another example calculation video later this week. And that's it for the main part of this course. Next week we'll talk about some niche topics, maybe lasers, maybe little quantum optics. And we'll see you then.